we will see the things related with XNOR gate. And the symbol of XNOR gate is like you are representing with XOR gate with bubble in front of it. Because whenever you are taking two inputs, that is A and B, at your output side you are getting A XNOR B, and this is the notation for XNOR. And basically the formula for this one is A B plus A bar B bar. Okay. And like when you draw the truth table for this one, so basically you have two input variables A B and one output variable which is Y, and all possible combinations are 0 0 0 1 1 0 and 1 1. And if you check by substituting A equal to 0 B equal to 0 in this relation A B plus A bar B bar, so for 0 0 you will get 1. Okay, and if you substitute 0 1 you will get 0. If you substitute 1 0 you will get 0. For substitution of 1 1 you will get 1. I compare this one with the truth table of XOR gate, and it is totally opposite. Okay. So this one is totally opposite, and that's why we are saying that whenever you are doing not of A XNOR B, you will get A XOR B, and whenever you are doing not of A XOR B, you will get A XNOR B. If you want to prove this one, so basically you need to write A XNOR B whole bar. So A XNOR B whole bar is nothing but A bar B bar. This one. Okay, so when you break this bar into its two components, this will be AB bar dot A bar B bar whole bar. And if you break this bar also, you will get by De Morgan's theorem, you will get A bar B bar dot A bar bar plus B bar bar. And if you write this A bar bar equal to A, this will become A bar plus B bar dot A plus B. Okay. So if you like open this bracket, then this is basically A bar into A plus A bar into B plus B bar into A plus B bar into B. And A bar dot A is 0, B bar dot B is 0. That's why you are getting A bar B plus A B bar. Okay, and this is nothing but A XOR B. You can prove in this way, like whenever you are taking complement of XNOR, two input XNOR, basically you will get two input XOR. And whenever you are taking complement of two input XOR, you will get two input XNOR. Okay, so this is basically a proof from like Boolean algebra, and this LHS is the proof from your truth table. And this XNOR gate, which is exclusive NOR gate, you can represent in SOP and POS form. So like if you want to represent in SOP form, you need to deal with these ones. Okay, so for this one, this A and B are 0 0, so you need to write A bar B bar. For this one, A and B are 1 1, so you need to write AB. Okay, if you are writing in POS form, then you need to deal with this 0. So if you are dealing with this first 0, that is your A is 0, B is 1. If you deal with this second 0, that is your A is 1, B is 0. Okay. So basically, if you write this first one, A is 0, B equal to 1, then you will get A plus B bar. And dot, when you write the second one, A equal to 1, B equal to 0, so you will get A bar plus B. Okay, so these are the expressions in SOP and POS form for this XNOR gate. Okay, so after like having information about two input XNOR gate, we can also like interpret this XNOR as an inverter or as a buffer, like as of our previous case. So when like we want to design an inverter, so basically what you need to do, you need to take that XNOR gate, and give A as your one input and B as 0. And if you substitute in that one, AB plus A bar B bar, if you substitute B equal to 0 in that one, basically you will get A bar at your output. That means that whenever you are giving 1, you will get 0 as your output. Whenever you are giving 0, you will get 1 as your output. So this is working like an inverter. Okay. So in the in second case, you can use that one as a buffer also. If you want to use this one as a buffer, you need to take this XNOR and you need to connect one input with A and second one is 1. And if you are doing this thing and if you are taking B equal to 1 and substituting it here, you will get y equal to a. Okay, so that is basically y equal to a, which means that if you are giving 1, you will get 1. If you are giving 0, you will get 0. Okay, so either you can say this thing as like this pin is working as a control pin. Right? So whenever you are giving this pin as a 0, it is working like an inverter. Whenever you are giving this control pin as a 1, it is working as a buffer. Okay, so with this you can use this XNOR gate as an inverter and buffer also. Let's come to like two input XNOR cases when I do XNOR of A XNOR A. Okay, so like this thing you can realize with this truth table also. Like when your two inputs A and B are same, what you are getting is 1. In the first case also it is 0 0. In the last case also it is 1 1. And in these two cases only you are getting 1 as your output. So basically this A XNOR A is 1. And the same thing is applied here also. Like this 1, if you write here, you will get A here. Okay. So you can prove that thing by substituting those values in your standard relation when A B as your input and A into B plus A bar dot B bar as your output. You can substitute these values in that relation and you will be able to prove that. Okay. So if I do this, basically this is basically A X NOR 1 is A. And the second thing is when the two inputs are different. So different means if I am taking one as A, then another one is A bar. So if you go with your truth table, you can find out that this is basically 0. And the same thing is applied here also. Like if you do A XNOR of 0, it is A bar. Okay, let's come to the thing like when multiple inputs are there of same type. If I do A XNOR A, that is equal to 1, you already know. What will happen if I do A XNOR A 3 times? Okay, so we will see this thing like we want to analyze what is A XNOR A. So I already know that A XNOR A is basically 1. So this is basically 1 XNOR A. Okay, and 1 XNOR A you already know from here, then 1 XNOR A is basically A. So this is nothing but your A. So if you write this one, this will become A. Now what happen if I take 4 variables, same variables for XNOR. Okay, so if I write this 4 one, so like A I want to XNOR with A, then again I want to XNOR with A, then again I want to XNOR with A. So this first one is nothing but 1. This second one is nothing but 1. So basically I am doing 1 XNOR 1. And whenever two inputs are same, you will get 1. Okay, so this one is nothing but my 1. In the same manner, if you prove for like if 5 A's or 5 same input variable, it will become A if you prove in the same manner. So in general, I can write this thing in a way like if I am taking any expression y or b, and if I am doing XNOR n times, okay, then it can be 1 or it can be y itself. Like I'm getting 1 means this n is even, and if I'm getting y means if this case is possible if n equal to odd. Okay, so these two things are there with XNOR gate. You already know the relation between two input variable XNOR and XOR. The relation is what will happen if I take 3 inputs. Okay, 3 input variables. So the thing is, if I take 3 input variables, which is A, B, and C, and if I want to represent this one in the form of XNOR, okay, so this will become A XNOR B XNOR C. Okay, so XOR of 3 variable ABC is equal to XNOR of 3 variable ABC. Now, if you want to prove this one, you can do it. So at present we are dealing with XNOR, so I am taking this one A dot B dot C. Okay, so like first I need to deal with this. So this is basically A bar B bar plus AB XNOR C. Okay. If you expand it further, you will get A bar B bar plus AB bar and C bar plus A bar B bar plus AB dot C. Now I want to apply De Morgan's theorem in this first one, and after applying De Morgan's theorem I will get A bar B bar whole bar dot A B bar, okay, dot C bar plus this one is as it is A bar B bar AB dot C. You can do in another way also, like you are doing XNOR and complement of XNOR, and this will become nothing but A B bar plus A bar B. I can write it as this. Then this is C bar plus A bar B bar plus AB dot C. And when you open this bracket, basically you will get A B bar C bar plus A bar B C bar plus A bar B bar C plus A B C. Okay, and these things are nothing but, if you represent these things in K map, this is nothing but 1 1 1 1 at these four places. Therefore, I am writing this as A XOR B XOR C. So with this, what I have proved is this one is equal to this one. So if you take it further, like we have proved for 2 variable, 3 variable. Now if I take 4 variable, okay, if I take A XOR B XOR C XOR D, 4 different variables, and if they are in XOR form, the relation is nothing. But if you prove, you will get A XNOR B XNOR C XNOR D whole complement. Okay, or you can write it in a different manner also. Like if you take complement of this one, if you take complement of this one, you will get A XNOR B XNOR C XNOR D. Okay, and these things also you can prove in a similar way. Okay, this one and this one. So with this, like you can say in generalized way, whenever I am having 2 different variables, okay, 2 different variables. So basically XOR and XNOR are complement to each other. Whenever I am having 3 or odd different variables, XNOR and XOR are basically same. Like this is the case for even, and where this is the case for odd variables. Okay, so with this, the concept for XOR and XNOR gate are over. The first one, suppose I take this A bar XOR B, and you need to prove that one is A XNOR B. Okay, so like whenever you have 2 inputs X and Y, okay, and your function is in the form of X and Y, and if you are doing XOR, so basically what happened, you have XY bar plus X bar by. So in this case, you can replace X with A bar and Y with V. This will become A bar B bar plus AB, and this is nothing but A XNOR of B. Okay. So in this way you can prove this. And let's take one more example. Like if I reverse this thing, if I told you to prove this one, this is also equal to A XNOR of B. So in this case, you need to follow the same steps, but the thing is, in place of X you need to write A, in place of Y you need to write B bar. So you will get AB plus A bar B bar, which is directly you can say that is A XNOR B. These are some examples where you need to prove the conversion of XOR into XNOR and XNOR into XOR. So with this, I hope XNOR is clear.